For our first exercise, we're going to use the 3-position switch to do essentially the switching that an H-bridge would do, and we'll do it though in a mechanical way. And we have the H-bridge drawn here schematically, and I wanted to do that first, but let me show you in industrial symbology. You're going to use more often and more likely you're going to see symbols that are used in ladder diagrams, and this is actually the way you would draw the normally open contacts. I know it looks like a capacitor. It is not. They kind of share that. That's the symbol for normally open contacts. You know, simply this. Normally closed contacts have a line through them. Okay. So here is the switching that we need to occur to get the motor to go in one direction or be off in the center position or go the other direction. And then the other thing we want to add is some indication for the operator. So we're going to have maybe some lamps that we can illuminate to show the different directions. So let's put on here. We know what's going to happen. We're going to, I think you remember. You know, we got those two contacts will close, and when they close, right, we've got this polarity connected to the motor, and then we've got these two close alternately, and we would have this polarity connected to the motor. We want to be able to see that on the panel, that it's actually happening. And so I think for this first exercise, we'll just do a very simple idea, and that is to have a lamp with, this will be our common, this will be 0 volts here. But look, that's pretty easy, isn't it? If we just put a lamp there, it'll have 0 volt side connected. So when you get 24 volts here, this lamp will light and indicate that this polarity is on the motor. I mean, in the other case, when the polarity reverses, you'll just have 0 volts here and 0 volts here on both sides of the lamp. So no harm done there. And likewise, we can put a lamp, an indicator lamp here, connect an indicator lamp to show us when the motor has the blue polarity, right? The positive on this side of the motor will light up this lamp. So here we have a forward and a reverse indication scheme, albeit a very simple one, but that'll be just fine. One thing nice about those lamps in industrial controls, you're always wanting to think about what the indicators are actually indicating to you. And this is pretty good indication. It's telling me there is a positive voltage here. I mean, I could put that lamp somewhere else. Let's say I had some relay controls down the road. You'll see more of this. I could have the lamp indicate by the set of contacts on the relay, turning it on. But then you have to ask yourself, what does that lamp indicate really? And the answer to that would be, it indicates that the relay has been actuated. It indicates that the contacts of the relay have closed. But does it truly indicate that the motor got that voltage that it was supposed to? Not necessarily. A wire could be broken, for example, or something could have failed. So, I mean, just a little thought while we're starting off with this whole industrial control thing. There are those kind of mindsets where you want to ask yourself always very precisely, what does an indicator indicate? And so these are pretty good because they'll still tell us, yes. And when I see that lamp lit, if I have that lamp connected real close to where the motor is, and that's why you'll have good proof that the motor is getting voltage. At least that's why we put sort of dual contact at the motor. If you have a portable trainer, you'll have to wire your motor into the box. Just bring it in to where you see those dual terminal blocks. And we purposely want the motor to be connected to a point that we can connect other things to it. So that's the idea. So this would kind of tell you at least that you have voltage to that point on those contact blocks or those terminal feed throughs. So that'll work out pretty good. I mean, you could be more elaborate. You could take wires, sense wires all the way out to the motor. We don't have to go that far, but yeah. But it just reminded me, we do want to be thinking, precisely what's being indicated. Yeah. Some other industrial mindset type things that we'll try to remember to talk about. Redundancy is a big one too. Let's look at what we have now. We've got indication for forward and reverse. Let's ask ourselves, do we have indication for stop? I mean, kind of. And the reason I say, you might say, what do you mean kind of? If the lights are out, it's stopped. Can you think of a scenario where that could be a false indication though? The operator sees both lights out, and so I'm going to say he assumes that there's no voltage at the motor. But that could be a wrong assumption. What other reasons could a light be out? A bulb could burn out, right? A wire could have come loose for the actual indicator. So you would call the kind of indication that we're talking about where both lights are out, then there's no voltage. That's more of a negative indication. But another good mindset with industrial controls is we'd prefer positive indication. In other words, we want something to be positively indicating that the motor is got no voltage, and then we don't have to rely on the fact that both lamps are still good and connected. So, and it might be hard to get completely foolproof positive indication, but we can put another system in place, and then not only do we have something that I would probably put in a classification of positive indication, but I would also say we have a little bit of redundancy so we can check one thing against the other. And so let's try to see what we can come up with. One way I could get a stop lamp indicator to light up would be to bolt 2 normally closed contacts in addition onto the back of this 3-position switch. Because, now when the switch is in the center position, neither plunger is activated and both of these contacts will be closed. And what would happen is I would just wire them in series with a stop lamp indicator. Okay, we're not going to do that. I'll show you why. Let's draw it. We could do the, we could take the 2 normally closed contacts right in series with each other. So the switch has to be in the center position for those to both be closed. And then we could put a little lamp indicator, and we could grab 24 volts here. Now that lamp will indicate when the switch is in the center position. But that's precisely what it will indicate. It'll indicate the position of the switch. So if you really ask yourself, what is this light indicating? I would say you have to give it that answer. You can't say that this light is indicating that there's no voltage here. It's indicating that the switch actuator is in the middle position. And most likely there's no voltage here then. But, let's say one of these contacts, for example, is been stuck, closed. And the actuator returns to center, but the contacts got welded shut. They got, stuck. This lamp won't indicate that. This lamp will indicate it'll be off. I mean, it'll be on, saying it's on. The motor has no voltage because it's on, telling you that. We would use like a red lamp to say everything's off. In fact, it's not off. Now, you would probably see some odd scenario where this light would be on in contradiction to this light also being on, and you would have a hard time knowing which to believe. So that would raise some flags. Of course, if this lamp was burned out, you could conceivably have this lamp on and this one out, and that would be a bad scenario. So these are the things that can happen, and you want to try to design a system that even though there's going to be faults that occur, you try to make it as foolproof as possible. In other words, it won't fool somebody because of your design. So let's see, we can improve on this for sure. If you want indication of the switch position itself, well, then this would be a good way to do that. But we're going to do a little better. Remember, we're trying to find some positive indication for the fact that there is no voltage across the motor. This is positive indication that the switch is in its centered position, because we're just following these physical contacts. Let's try to get some positive indication that there's no voltage present at the motor. So we're not going to use this, but what we are going to use is a sense relay, and we're just going to attach the coil of that relay, and that would represent the coil in ladder symbology. You just put that right here too. So we have the coil of a relay, and then we'll just use some normally closed contacts of that relay to be our to connect a lamp indicator. So this is how we'll do it. So now we have positive indication because of no voltage existing, because if there's no voltage across the motor, this coil will be off, those contacts will be closed, that lamp will be on. And that's a good positive indication. And it's also redundant. You know, you're a little more certain now that you don't have voltage there if both lamps are off. But just in case a lamp burned out or a wire came loose, this lamp is on to show you also that there's no voltage across that coil. And I mean, yes, you can keep going with your thoughts. I mean, yes, if a wire came loose here, this light could come on even when there's voltage here. But at least you have that redundancy to help you spot that there's something goofy going on, you know, like a wire came off. Because if you have a lamp indicating showing a voltage here, but you also have a light showing that there's no voltage there, you got to investigate then. So the kind of positive indication is a good starting point, and then redundancy helps you out too. It's all part of this industrial design. I think you can see the relay that we need mustn't have any polarity, because it's going to have both polarities. The coil is going to be subjected to reversal of polarity. Now, relay coils don't have polarity as they, by themselves. It's just a coil. The magnetic field can be either direction, and it'll still pull the relay contacts in. The thing that might give a relay polarity is if you start adding things like a freewheeling diode, that diode that shunts the kick from the coil when it turns off. If you add a freewheeling diode, it now has polarity, because that diode will short out in the opposite polarity. Or if you add an indicator LED, it could possibly now give a polarity sensitive nature to the relay coil, because the diode, the LED, has polarity. And of course, if you have both, you got two reasons that the relay now has polarity. So some relays do have polarity because of indicator LEDs or freewheeling diodes that are included. Now, what we need though is a relay. We still want the freewheeling diode. We still want the indicator LED. So if you remember last year, we had mentioned a really nice way to get everything you want is to front end the relay coil with a bridge rectifier. And in fact, the one that we have here does exactly that. So in the case here is some circuitry. There is a bridge rectifier first, and then the relay coil and an indicator LED. So that's what we've got to work with. And you'll have the pinout for this. There is a data sheet posted in the files tab, but since I have it right here, there's redundancy here. These are both the same thing, same point here. A1 and A2 are the place to power up the relay. I did not say they're the relay coil, because in fact they aren't. They're the input to a bridge rectifier and then the relay coil. But yeah, so it doesn't matter which polarity you put positive or negative. Obviously, it doesn't here. It's going to get both. There is a convention. I'm trying to remember it. I think A1, if you have a relay with polarity, I think A1 is the positive, but we can double check that. But this would be where you'd, this would be what you'll connect across the motor, A1 and A2. And in fact, let's take a look here. These are not screw terminals. So these are that other type that I showed maybe in the terminal blocks video. And you'll see you actually insert like a screwdriver blade in here. And then there's a sort of a lever action that opens up the clamp. So let's see if we can, I don't know if we can see that or not, but we'll see if we can try. Okay, so there it is, open maybe. And then I shut it. Well, I'm starting to pop the whole case open here. But yeah, so you'll have to pull that back, and that's how you're going to do the wiring for these. I don't know if I can show that better. There we go. See how I'm opening it? There it's kind of the clamping shut on the wire, but here it's open, and then clamp shut, open and clamp shut, open and shut. Okay, so we have that all the way around, and you could pop the relay out if you wanted to inspect it. There's a little schematic symbol on top. It's a little washed out, isn't it? So it does show a single pole double throw, and in fact that is what we have. Even though you see 6 pins, these pins are the same point internally. They're the same piece of metal, so it looks like it would be a double pole double throw relay. Wouldn't be a bad guess just looking at the pins. However, you'd be wrong. It's actually a single pole double throw, a single pole double throw with redundancy on the pins. Okay, so, and these points are all redundant as well. They're the same points, but and you can check it out when you power it up, but I think you'll find the terminal 11 is the pole, and then I forget which one is normally closed, but 14 and 12, one of them's normally open and one of them's normally closed. So you can investigate that with your ohm meter, or look at the data sheet in the files tab. Yeah, and there's your indicator light there. So this is the relay that we'll use to sit across the motor, and when there's no power, we'll use the normally closed contacts to connect 24 volts to a red indicator lamp saying that there's no power at the motor. And maybe just one last thought. We have this design, which we have indication, I would say, of whether voltage is present at the motor or not. If we wanted indication that the motor's actually spinning, this wouldn't really suffice. I mean, just the fact that the lights are coming on, that doesn't mean the motor's actually turning. So yeah, you would have some kind of a encoder that's actually attached to the shaft of the motor, and it would give you that kind of information. It would give you indication as to not just that it's turning, but maybe the speed that it's turning, and maybe the direction, of course, that it's turning. So those would be more indicators that you would add. And not that you would throw these indicators away. These are still good indicators that it has voltage applied to the motor. You could have some indication like this coil is a really good one just to have sitting right at the motor contacts. And then you can see if the motor's not turning, it's probably the motor's fault, because if it has power, but it's not spinning, then it probably is something like maybe a bearing that went out, or who knows. But you would use these kinds of indicators in conjunction with each other. So it wouldn't be one or the other. It'd be both. It would be the answer. So in a control, industrial control scheme, most likely you would have the encoder telling you, actual rotational information, speed, direction. But you would also have indication from like a relay that tells you it's getting power and so on. Makes it ideal for troubleshooting. You don't have to actually even necessarily be out there right at the point of failure to see what's failing. You can sometimes troubleshoot things just if you have the right sensors, watching the right things. And that is today's industrial automation world. More and more, just everything's monitored. So you don't have to guess. You don't have to look around, walk all over the plant trying to troubleshoot. You've got sensors on everything. So, I mean, like, for example, they'd have temperature sensors on every bearing. So if you would, just to keep our little example going, if you would see that these indicators show that it is getting power, but the encoder shows that it's not rotating, you might pull up the history of one of the temperature sensors on the bearings. And you might see very quickly that there's a bearing that was running hot and overheated, and you can see the whole histogram of the temperature of that bearing. So yeah, so sensors everywhere, and that makes troubleshooting, a lot easier if you know where to look. So this is our first exercise, and it's just intended to get you started, kind of get you oriented on how to put together industrial switches, push buttons, lamps, even just physically, just get the hang of that. How do you put them into a cabinet? How do you attach wires to them with the terminals and a screwdriver and so on? You can use ferrules if you want to. I don't know that you have to, unless the wire's too thin. I mean, the kind of your call on that, and you'll be able to see. I mean, if you put a wire in here and after clamping down, with your screwdriver, I'm not really using the right screwdriver. That's not a good demonstration. Let's get the right screwdriver in there. But yeah, I mean, if the wire pulls out, obviously maybe you needed a ferrule if it's too thin. This stuff's just temporary. The stuff we're doing, we're going to, undo the wiring a lot, so it's not so critical to use ferrules. But ferrules do make life easy because they terminate the wire itself, and then you just drop that ferrule right into place. It does work nicely. So it's up to you whatever you want to do. Do some ferruling. You don't have to do all your connections with ferrules, though. Okay, that's our first exercise, and we can actually implement that, and I'll work up videos on future exercises.